Sorry.
All right, this is my part, okay? Can you guys hear me?
Yeah.
Yes.
Yes, sir.
All right.
Clear now.
So we're going to be talking about radioactivity, and radioactivity is the decay of an unstable nucleus, and there's three forms of it. We're going to start with alpha decay, which is the emission of two protons and two neutrons from a heavy element. And two protons and two neutrons, like in that video, you can see that that's helium-4. So it's pretty much just turning into large and heavy objects being emitted. And as far as penetration goes for safety, it's not in the slides, but they're not that dangerous. You just don't want to ingest or inhale them, but they can be stopped by paper or human skin. And then you have beta. Beta decay is the emission of an electron when a neutron in the nucleus decays into a proton and an electron, also a neutrino. But that is smaller and lighter than alpha radiation, and that means that they can penetrate further, but they cause less damage per interaction because of the lower weight or mass. And the penetration, because they can go further, they can go a few millimeters of plastic or a few feet in the air, and that can lead to radiation burning on the skin or tissue damage. But then you have gamma radiation or gamma decay, and that's the emission of a gamma photon when an excited proton in the nucleus transitions to a lower energy state. And that's kind of different than the rest. It's not a particle, but it's a high energy photon or an electromagnetic wave. And these are different than the rest, and they go pretty deep. And these are the ones that we actually need the concrete or the lead to actually protect against. So that separates it from the rest. So next slide, please. And this is a graph depicting what I just explained to you. So if you look at the top, that explains alpha. And as it decays, it goes into the new isotope, which is known as the daughter isotope, along with the two protons and two neutrons, which you can see is helium. So that is what we know as alpha radiation. And with beta radiation, it is the emission of high energy electrons for beta minus or positrons for beta plus, but those are two different things. But in this graph, you see how it degrades and forms the daughter isotope, and it emits the electron. These are used in a lot of other uses, but we're not going to discuss those today. But on the bottom, you see the third one, which is gamma, and it degrades and it emits gamma radiation or photons, whatever you want to say. But these are the three things, and these are the three ways that natural radioactivity occurs. And most decays of heavy nuclei proceed by alpha decay first, leaving a nucleus with excessive neutrons, which will likely undergo beta decay. Then beta decay occurs, and alpha decay can leave one or more excited protons in the nucleus, which will ultimately result in gamma decay, to restore balance. And heavy elements gradually decay into lighter and lighter elements down to the most stable nucleus, which is iron. And there is a 50% chance of a nucleus decaying in a specific time period, which is unique to the nuclear state. This is what we call half-life. So a typical scale contains 10 to the 26 atoms. On that scale, we can be confident that half of the sample will decay in the specified time period. That is what we call the half-life. So carbon-14, its half-life is 5730 years. That's it being half as good, So it would take, in theory, twice as long as that for it to have another, and then twice as long as that to have another. And it's like a gradual scale that goes fractional, because it's just half times half times half times half. It just gets smaller and smaller over time. Okay. And plants and animals developed in the presence of small levels of radiation from heavy elements and radiation from space. This is what we know as natural background radiation. To some extent, we all have mechanisms that counteract the effects, but long-term damage to the cells from radiation is frequently the source of cancers and aging. You can't repair cells that are permanently, damaged. So just like computer code, it just keeps on having bugs. Next slide. And so this is the example. So based on the half-life we were talking about, suppose carbon is extracted from a fossil and it's found to contain a quarter of the carbon-14 by percentage as a living organism. When would you expect the fossil to have been alive? So it would be a little bit easier to do the math if it had the carbon 14 in the actual example, but all you have to do to find this, if you have the amount of years it is for the half-life, is for the half-life, that's 1/2, right? So you just have to multiply the denominator twice to get to a quarter, and that will give you the amount of years time. So if you can hit spacebar or what have you, it'll probably reveal, there you go. So if you look at this, you'll see that 2 half-lives have passed. So the sample is a quarter the percentage of a living organism. So you can calculate that it was approximately 11,460 years since this organism was living. And I think that concludes my part of the presentation. Thank you, guys.